so first I want to remind you that there is a test coming up, the midterm test. So if you care about your grade, please come and attend the test. To the people who are watching webcast, so I want to remind you two things. So number one is please make sure that you can find the lecture theater because if you are not familiar with where LT32 or LT26 is, it takes a while to find it. So please check your map or make sure that you'll be here on time. Okay, so this is one thing I want to remind you. Another thing is we are going to use bubble form. You have to use pencils. So please bring pencils because the ball pen or pen, somehow the machine could not read. So you have to bring the pencils. Okay, so, and also I have sent an email remind you that which lecture hall you will be sitting, right? Because this lecture hall can only hold half of the audience. So please do check which lecture hall you are sitting. And if you couldn't find your name there, it's probably because of the name was listed based on tutorial groups. So if you couldn't find your name there, probably it means you didn't have a fixed tutorial group. So please email me so that I'll assign you a tutorial group and tell you which lecture hall you will go. Okay. If you have any other questions about these kind of things, ask me, email me or ask me. Okay. All right, so so today I want to instead of talking about a new topic, I want to do some revision. So the revision will be based on the last semester midterm test. As you can see that they cover lots more topics than we do. But, well, anyway, so you are going to see those topics in the second half of the term. Okay. So I'm doing this because somehow I receive lots of emails and people ask me. So I think it's better we go through it together once rather than I have to reply hundreds of emails about individual problems. Okay, so let's do these things together. And if you have questions, stop me and ask me. The second half will be devoted to it's like office hour. So if you have questions, ask me. I'll be here because it's hard to find a common time for all of us. So if you have questions about lecture notes, tutorial problems, whatsoever, ask me, okay? All right, so let's start. So in the previous midterm, the last semester, so it's all true or false. Okay, so here's the first question. Suppose you have two subsets of a universe. So X is the whole set, and A and B are subsets of X. So the question asks you whether this equality holds. So the set A is a union of two parts, A intersect B and A intersect B complement, where this B to the power of C stands for the complement of B in X. Okay, so this is a question about sets, Venn diagram and so on. So the answer is true. And well, in the test, you are not asked about reasons, but let's make sure that we know why it is true. So you can think of this way. Of course, you can think of other ways. So since the whole universe is B and its complement, right? So it's either in B or not in B. So two parts. So we can see that the set A, we start from left-hand side, A is A intersect X. This is because X is everything, right? A is part of X, so when you take intersection, you get the smaller things, which is A, right? So A is A intersect X, but X is B union B complement, so we get A intersect bracket B union B complement. And then you can use, this should be distributive rule. So I'll change this. So it's distributive, right? So the intersection, you can distribute A intersect B, A intersect bracket union into, you distribute A to B first, and then distribute A to the B complement, right? So you get this, but that is the right-hand side. So I'll change this. So last inequality is because of distributive rule. Okay. Is it clear? Should I draw a Venn diagram? I'll see. So does it work? So it's quite straightforward, right? So this is our universe X, and any set B will split the universe into B and B complement, right? To the left of this blue line is B. To the right of the right of the blue line is B complement, right? So now you have a set A somewhere here. So the equality just says A is this part, which is A intersect B, union the other part, this part. This is A intersect B complement, right? So from the Venn diagram, is quite obvious. Okay. All right, so that's question one. So now let's go back to the test. Okay. Here, surprisingly, there are many people asking this question. So first, okay, so let me read the question first. So the questions ask, okay, if we have to decide whether this is true or false. So if there are infinitely many even prime numbers, then this guy, 148, is an even integer. Okay. So first, let's understand everything, every word in this statement, right? So prime number, do we know prime number? Prime number are those integers which can be divided only by itself and 1. Let's say positive integers. For example, 7, right? 7 you can only divide by 7 and 1. No other factors. So 7 is a prime, okay? So we know prime numbers. Now, even, so this even is not an adverb. So this even means the prime number which is even. So this even and that even are the same. So the even integer means like 2, 4, 6, 8, all these even numbers, right? So it's a multiple of 2. Okay, so prime number we know, even number we know. Okay, now here infinitely many. So the first part says if there's infinitely many this kind of number, and then this guy 148 is an even integer. Okay. So what's the purpose? What is this problem testing? So the problem is testing the truth of if then, right? So we learned that we have learned how to evaluate compound sentence, right? Suppose you use connectives to put two sentences together, and then how to decide the truth value of the complicated sentence, right? So this statement is of this form: if P, then Q, right? So it's if P then Q. So the question is testing whether you know how to evaluate the truth of if P then Q. Okay, so this is the purpose. Okay, so now in order to decide if P then Q, we have to know whether P is true or Q is true. We have to know what happens for the simpler sentences, right? Now, Q is easy. 148 is an even integer. So this is obviously true because this guy is a multiple of 2. So Q is true. Actually, if you know Q is true, if you look at the truth table, this is already true. If P then Q is already true. P arrow Q is already true, right? But let's say we want to understand everything, right? So now, is P true or false? How many even prime numbers are there? Are there infinitely many even prime numbers? 0? No. We don't consider 0. You said 1, right? Yes. Okay. So there's only one prime, even prime number, which is 2, because all other numbers, all other even numbers has a factor of 2, so it cannot be prime anymore. You take any even number like 8, it has to be divisible by 2, right? So it cannot be prime anymore. So there's only one even prime number. So the P is false. Now again, if P is false, actually you don't need to look at Q. The whole if then is true. So this we have, how to say, we are over flooded by the information, but never mind. So the answer for this is true, okay? So the statement, okay, so the explanation is as follows. So the statement is of the form if, okay, I said P and Q, but okay, if A then B, right? So the A says there are infinitely even prime numbers, but it's false because there's only one, as somebody pointed out. And B is true, so if you look at truth table of this, if A then B, so you have F arrow T. But if you check the truth table, we assign to be true. Okay? So this is clear, right? By the way, you need to know, okay, suppose, so this question actually also tests you another knowledge. You need to know whether there are infinitely many prime numbers, because we said there are two nice theorems, right? Somehow everybody should know. Even for general education module, you should know. One is square root 2 is irrational. The other one is there are infinitely many prime numbers, right? So although there's only one even prime, but there are infinitely many odd prime numbers. Okay, so those things. So this also tests you some basic knowledge about numbers. Okay, so is it clear? Can we go on? Okay, now the next three questions, these are the, I receive more queries about this than others. So the next three questions deal with these three statements, P, Q, and R. Okay, so they are in English. So P says he is super smart, okay? Q says he knows all the answers in this exam, okay? And R says he's a great guy. So there are three statements about some person, okay? Now, question 3 says this, okay? The English sentence, he is super smart because he knows all the answers in this exam. So this is one sentence. Now, the claim is this sentence is the converse of Q arrow P. Okay, so the claim is the English sentence in the quotation mark is the converse of Q arrow P. Okay, so we have to understand what is converse, right? And we have to understand the English sentence in the quotation mark, what is the symbolic form? And then we can figure out, right? So, okay, so I guess the answer is false. The reason is Okay, so let's first figure out the symbolic form of the sentence in the quotation mark. Okay, okay, let's see. So he is super smart. So that's he is super smart because he knows all the answers in the exam, right? So this is the conclusion, right? He is super smart is the conclusion, and he knows all the answers in this exam is the reason, right? Because is the reason, right? So in the if-then form is if you have, so he knows the answer in the exam is Q. So Q is the reason you conclude P. Right? So from Q you conclude or you derive P. Right? So this English sentence actually says Q arrow P. Am I clear? So if something then something, okay. If A then B says A is a reason, B is a conclusion, right? So under the assumption of A, you conclude B, right? So exactly in this sentence, English sentence, the answer is the reason and super smart is the conclusion. So we have Q arrow P. Okay. So now, so what is the converse of Q arrow P? So converse is you just reverse the row, right? So the converse says P arrow Q, right? But question 3 says the converse is also the same. It's not correct. Is this okay? Okay, right? So I think as soon as you figure out the form of in the quotation mark, you know the answer. Of course, you need to know what is converse. Okay. So that's question 3. Okay, now question 4. Again, we look at the English sentence. So the English sentence says, just because he's super smart, it does not mean that he is a great guy. Right? So this is, again, a sentence in the quotation mark. We want to know whether this is logically equivalent to this form, P arrow not R. This squiggle stands for not. It's a negation of R. Okay? So we want to know whether these two are logically equivalent. So again, we need to figure out the symbolic form of the English sentence and then try to see whether they are logically equivalent. Okay. What's the meaning of logically equivalent? They have the same truth table, right? So, okay, so let's try. Well, the answer is false. Okay, so let's figure out the sentence, right? So the sentence says, okay, I want to change it slightly. So the sentence says, from P, just because he is super smart. He's super smart is P. Okay. So from P, we cannot conclude or we cannot derive R, right? It doesn't mean you cannot get this conclusion. Just from P, you cannot get this conclusion R, right? So this English sentence is in this form. From P, we cannot derive R. Okay, so in symbolic form is not the case. You cannot do it. Is a negation of P arrow R. Is this okay? So it's not the case. From P you can derive R, right? So from P you cannot derive R. So this says it's not the case that from P you can derive R. So this is exactly that. Okay, so now we have two sentences in two statements in symbolic form. One says not bracket P arrow R. The other one says P arrow bracket not R. Are these two logically equivalent? They have the same truth table? no, right? So if you, okay. So you can give examples. So what's the example? So this one is false only when P is true. This one, R is true, right? But this one can be false when P is false. So anyway, so if you draw truth table, is apparent. Okay, so okay. Now, if you are curious, you may wonder how to translate P arrow not R into English. So P arrow not R is from the reason, right? If he is super smart from P, you can conclude the negation of R. So the negation of R would say he's not a great guy, or he's a lousy guy. Right? So if he is super smart, then he is not a great guy. Or you can say something like a super smart guy never great, or something like this, right? So this is the meaning of this P arrow not R. Okay, so the answer is they are not logically equivalent. Okay, so now next one is more interesting, or I didn't cover this in this in this semester. So I'll tell you the reason in a second. Okay. Okay, so let's first read the sentence. So the sentence says this. So the sentence, not unless he knows all the answers in this exam is he a great guy, whatever it is. Okay, so here we have one English sentence, number one. Okay, so it says this. The difficult part is not unless. Okay. Now he claimed that this statement one is the contrapositive of statement two. So statement two is easy. Statement two says, if he is not a great guy, then he does not know all the answers. So this is not P arrow. This is Q. Huh? This is Q, right? So this is not P arrow not Q. Okay, so statement two is easy, but statement one involves the word not unless, which I never use in my life, but I don't know. Maybe it's very common for you. You use it every day. I don't know, but I never use it. Okay, so if I never use it, I look at dictionary. So according to Webster dictionary, so the not unless actually means only if. So if it's only if, it enters our territory, right? So we covered the word only if, right? So not unless P, comma Q actually means only if P, comma Q, right? So we learned how to decode this, how to write this guy in a symbolic form. So this is different from if P than Q. So it's the other way. So therefore, so this guy is actually Q arrow P. So this is something you need to know. The only if, how to turn the only if into a symbolic form. And this we have covered it, and you should know. Okay? And suppose you didn't look at a dictionary. Okay, so in the previous, I checked the lecture notes in the previous semester. So the lecture explained in this way. So there's an alternative way of explaining the meaning of not unless. So according to the lecture, well, I guess probably this is according to our understanding. Not unless P I do Q means unless P I do not do Q. Okay, again, too many not. Okay, so the meaning of not unless means this. Okay, so not unless P I do Q means unless P I do not do Q. Okay, and in the tutorial we saw unless means if not, right? So the whole thing is if not P, I do not do Q. If not P, then not Q. Okay, so it's not P, arrow, not Q. Okay, so this is equivalent to Q arrow P. It's the same, right? So we get the same conclusion. Okay, so in short, the reading of unless is like this. Okay, so we know how to turn this into a symbolic form. Okay, so now why I didn't cover this in this lecture, because first I never use it. Okay, and also there's another reason. So actually if you learn logic, or you study mathematics, right? When you take negation, you usually take negation for a full statement, to a whole sentence. You don't take negation for a word. So we don't study not unless, because not unless is not, how to say, unless is a word. It doesn't claim a fact. So it's hard to, unless there's no truth value. So you take negation, there's still no truth value. So when we take negation, usually we take negation of a statement, means the statement will have a truth value. It's either true or false, right? So for this reason, I don't want to emphasize these things, right? Although in real life, probably you have to deal with this. But in logic or in math, we usually take negation to something has truth value. Otherwise, what is the meaning, right? So in mathematical logic, or in math, or in logic, negation usually applies to a statement, to a sentence which has a truth value, right? Usually we do not apply it to a word. So that's the reason I do not want to emphasize this. Okay. Questions? Is this okay? Reasonable? Okay. So the answer, now you know it. So okay, so I hope you remember these. So the first one, translate to, is it Q arrow P? And no, so it's R arrow P, right? So he is a great guy is R. So therefore the translation of this into R arrow Q. Q says he knows the answers. So the whole thing is R arrow Q. But the second sentence we just saw translate into not R arrow not Q. So is this guy, not R arrow not Q, the contrapositive of R arrow Q? The answer is no, right? So therefore, so this is F. Okay, so because the contrapositive, right. So the contrapositive of second sentence means this. Maybe I should make it clearer. The contrapositive of this one is Q arrow R. So therefore, it's different from this. Okay, so the answer for this question is false. So this is probably the most complicated among these. Okay, questions? You can ask me later, okay, if you have questions. Okay, now this is another interesting topic. Somehow I didn't cover it in the previous lectures, but I should. So this is something very nice to know. Okay, so I'll take this opportunity to cover the topic I missed. Okay, so here, so the question is, if f is a surjective function from A to B, but the set A and set B are finite sets. Finite sets means it has 5 elements, 7 elements, or it has a finite set, like 100 elements, and so on and so forth. Okay, so suppose you have a surjective function from A to B, and A and B are finite sets, and they have the same number of elements. For example, both of them have 100 elements, or both of them have 2,000 elements, right? So f is a function from A to B, where A and B have the same number of elements, they are finite. Okay, so this is a condition. Now, if f is surjective, and then f must be, it's necessary, it must be injective as well. Okay, so this is a bit harder, right? Okay, so it means surjective function from A to B, where A and B have same finite set, finite size, it must be injective, right? So surprisingly, the answer is surprisingly, not surprisingly. So it's true. Okay. But the reason is more, okay, it's better to justify in this way. Okay. You may justify it in other ways, but this is a typical way of doing it. And this boldface words, these words are what I missed in the lecture. I should have covered. Okay. So I claim that this is a consequence of something called pigeonhole principle. So shorthand is PHP, pigeonhole principle, okay, PHP. In mathematics, it says this. Suppose you have two natural numbers, m bigger than n, like m is 3, n is 2, something like this. Right? And f is a function from this set. This set have m elements into n elements. Right? The conclusion is f cannot be injective. You cannot send different things to different things. Well, this looks too mathematical, but the reason why it is called pigeonhole principle is very, very intuitive. So the name comes from this example. So suppose you have m pigeons, and you have n pigeonholes. But somehow the number of pigeonhole is less than the number of pigeons. Right? So m is bigger than n. So for example, here you have 2019 pigeons, and you only have 2018 pigeonholes. So to say this guy is never injective means you must hit the same pigeonhole at least, right, so you must have at least two pigeons share the same pigeonhole. This is very, very intuitive, right? Because otherwise, where does this guy go? Right. Okay? So can you see the connection? Right? It's the same, right? So here it says, suppose you have more pigeons than pigeonholes, then at least some of them will share. Right? You cannot have one-to-one. You cannot have injection from pigeons to pigeonholes. Right? So this is very, very intuitive. Okay. Now then I'm going to use this pigeonhole principle to justify my answer. So not only that, I'm going to give you a slightly more general versions. Okay, so I want to say that, so I'll give you two applications on these surjective, injective, and so on and so forth. Okay? So the first conclusion from pigeonhole principle is this. So let A, B be finite sets of the same number of elements. Okay, so suppose you have the size of A is the size of B. They are finite, and it's equal M, like 2019 or something. Okay. So now if F from A to B is injective, then F must be surjective. If it's injective, then it's surjective. Okay, so again, too abstract. Think of pigeon and holes. Okay. So suppose you have m pigeons, that's the number of elements in A, right? And m pigeonholes, that's the elements in B. So F from A to B, F must give every pigeon a place to live, right? Assign pigeon a hole. Okay. So now if F is injective, it means no pigeon share the same hole. Right? So the conclusion is you must use all the holes. You cannot you cannot skip any pigeonhole. You see what I'm saying? You have m pigeons, m pigeonholes. Suppose there's no sharing, then you have to use all the m pigeonholes. Otherwise, I mean, you don't have enough space, right? So this is quite obvious. From pigeons and pigeonholes is quite obvious. Now, suppose you want to prove this in a function form, I don't know, you can use, this is one of the possible proofs. So you prove by contradiction, right? Suppose it's not surjective, then F will miss some point in B. So therefore, the range of F has less element than M because you miss some, right? Because the range is not equal to the codomain. So the number of elements in the range is strictly less than the number of elements in the codomain, which is M. So the range of F has n less than m many elements. But this F from A to the range is still injective because originally it's injective, then still injective. But pigeonhole principle says no. You cannot have injective function from larger set into smaller sets. Okay, if you don't like these two mathematical proof, just think of pigeon and holes, and then I'm happy. If you understand the second bullet point, I'm okay. All right? Okay, so this says, suppose F from A to B, and A and B of same size, finite size, injective implies surjective. The next application says surjective also implies injective. So this is the second application. So again, the same assumption that A and B be finite sets of the same number of elements. Let's say both of them have m elements. And again, F is a function from A to B, right? So this time, let's assume F is surjective. The conclusion is then F must be injective. Okay, again, the words surjective and injective are complicated. Let's think of them using pigeon and holes, right? The same task, M pigeons, M holes, right? Elements in A are pigeons, elements in B are holes. F will assign the M pigeon into the pigeonholes, okay? So the conclusion says, suppose F somehow managed to occupy every pigeonhole, and then there must be no sharing. You have M pigeon and M holes. Suppose all the pigeonholes contains a pigeon, right? This is meaning of surjective. Then you cannot have two pigeons share the same hole, because otherwise you have you only have M. You only have M pigeons. You cannot afford to sort of let two pigeons share the same hole, right? Otherwise, how can you occupy the whole M pigeonholes, right? So I think from using the language of pigeon and the pigeonholes is easy. Okay, so you see the picture, right? Okay, now the proof is a bit less clear than the pigeon and holes and pigeonholes, but let's go through it. Okay, so you may have a shorter proof, but let's try. So assume F is surjective. You want to show F is also injective. Now I read this first, and I will draw a diagram and show you what it says. Okay, so let's try this. So suppose for a contradiction that F is not injective. So what does it mean? It means you have x1 and x2 from A, and F send them to the same point. Let's say it is y0 or y0, where x1 and x2 are different points. Right. So if it's not injective, you must have two arrows shoot to the same thing. Okay, now let's imagine we can order elements in A so that x1 is less than x2. So let's consider sort of like inverse. So for each point in B, you trace back who shoot the elements in B, right? So for each, consider a function g from B to A defined by g of y equal x if the arrows start from x shoot to y. But in the case it is not injective, you may have several arrows shoot to the same y. But let's choose choose one, just pick one. Ignore the other ones, right? So you suppose there are many x hit the same y. You just choose the smallest x which hits y. So you define g of y is start x. And then g is injective from B to A because different point y will come from different point from. So by the application 1, G is surjective, right? Because injective implies surjective. But in this case, you miss x2 because you take x1. You cannot take x2. So I'll draw a picture. This looks complicated, but from picture is very clear, I hope. Okay. So here I have A. Here I have B. So they are the same elements, right? So let's say these are 1, 2, ... to m. So he has m elements, and here B also have m elements, 1, 2, ... m. Okay, so the F somehow send, so F will be a function from A to B, right? So for example, I send this. And let's say, for the sake, okay. So let's assume F is something like this. F is a function from A mapped to B, right? So our assumption says F is, we know that F is surjective. Right, so every black dot in B was hitting by an arrow. So we want to conclude that there's no such thing. So this I cannot have two arrows hit the same point. I want to show is injective. Okay. So now, what is the definition for G? So the definition for G is this. I look at every element in B. So for example, if look at 1, right? So I look at who shoot arrow to 1. So in this case, 2, right? So I will define my G. I will define G of 1 equal 2. So this is because F of 2 is 1, right? So if F from A shoot to 1, if F sending 2 to 1, G will reverse it. G will send 1 to 2. Okay. Now similarly, look at 2. G of 2 will be 1 because F of 1 is 2, right? So in this example, this is clear. So I send it back. Okay. Now here is the problematic part. Right? Suppose you have x1 and x2. These are 2 points in A, but you send them to the same point, y0, in B. Okay. Suppose you have x1 here, x2 here. Both of them go to this y0. Now, how do I define G? So G will choose between x1 and x2. But as I said, I choose the smallest one. So in this case, I will give up x2. I will define G of y0 to be x1. Okay? So in this case, I will define G of y0. I will define it to be x1. So this is because f x1 is y0 and x1 is the smallest. Because I have to choose. Suppose you give me 3 points, I choose the smallest one. Okay. So now you'll see the arrow of G, right? So arrow of G goes like this, and this guy goes to there, and the M will shoot to somewhere here. So you see, G is defined on B because F is surjective. You go back, okay? And different point in F, different points from so if you start from different points in B, you cannot hit the same point in A, because from this point, F can only shoot one arrow. You cannot shoot two arrows. So therefore, G is obviously 1 to 1. Okay. So now we have a function G from B to A, which is 1 to 1. By application 1, this guy should be onto. It should be surjective. But he missed X2 because from Y1 he can only shoot one arrow. Nobody is going to hit X2, right? So we miss X2. So this is a contradiction. Okay, so since we are not a mathematical course, right? So if you think this is too it doesn't make sense, right? Well, then just forget it, right? Try to understand these pigeons and holes. I think is more intuitive. Okay, so for pigeonhole principle, there are we can get other mathematically interesting conclusions. Maybe not very interesting in real life, but this is interesting in mathematics. So if I combine the two results I just showed you, pigeonhole principle actually tells us this. Suppose you have A and B, they are finite sets, and they are of the same number of elements, and F is a function from A to B. So the conclusion is F is injective if and only if F is surjective. So the notion of injective and surjective coincide in this particular case. So this is quite useful in mathematics. But it only applies to finite sets. If it's infinite set, you can find examples. And so that's why I highlight the finite. The finite is important. You cannot drop it. It doesn't mean for any set, injective means surjective. That's totally wrong. But for finite sets of the same size, it happens to be true. Okay, so that's some of the remarks on pigeonhole principle. In daily life, pigeonhole principle has this kind of fun examples. Okay, so here, I give you two examples. So suppose, so if you are at a reception attended by more than 367 guests, okay, can you be sure that there will be at least 2 persons with the same birthday? Okay, you have 367 guests. Can you conclude that must be 2 persons have the same birthday? Well, the answer is yes, right? So the reason is, think of the guests as pigeons, right? The date are like pigeonholes. Now the most number of pigeonholes are 365, but if you are, I noticed that some of our students actually born on February 29, so I must include February 29. So probably you have 336 pigeonholes. So I change the number to 367. If you have 367 pigeons, only have 366 pigeonholes, then there must be some sharing, right? So 2 persons must share the same birthday. Okay, so this is similarly. Okay, the next example is the same. Okay, more or less. So let's say a dating agency requires each of its clients to answer a questionnaire consisting of 10 questions with yes or no answers. Okay. Now they are this number, 525 male and 500 female clients. Can you be sure that there will be 2 questionnaires? There will be 2 questionnaire forms with identical answers. Right. So the answer again is yes, because how many possible different answers are there? So you have 10 true or false questions. So each question you have 2 answers. So you have 2 to the 10 many possibilities. So that's 1,024. But somehow the number of people we choose here happens to be 1,025, right? So therefore, there are at least 2 persons give you the same answer. Okay? So these are the easy examples for pigeonhole principle. Okay, so now that's the end of detour. That's the end of the pigeonhole principle. We come back to the test question again. Right? So let's finish off it. Okay, so the next question is about functions. So let f and g be 2 functions from a non-empty set X to a non-empty set Y. Now consider this set. The set A collects all the small x in capital X in the domain, such that f of x equals g of x. Somehow f and g hit the same point. Okay? So the claim is that A must be non-empty. So it claims there must be some point f and g send it to the same place. Okay. But this is false, right? It's probably easy to see it's false. You can look at some example like this, right? So x and y are natural numbers, so they are non-empty, right? So certainly not empty. Now, the f will send natural numbers to even numbers. G will send natural numbers to odd numbers. And then there's no common hitting, right? Then the set of A collect the points where f and g send them to the same point. Impossible, because f will only hit the even numbers, and g will only hit the odd numbers. So you can have much simpler example. You can choose some constant functions. For example, f all send everybody to 0, g send everybody to 1. Again, you don't have overlap, right? So you can have lots of examples. Okay, so is this clear? Okay, now financial math question. Hopefully you still remember this is our first the lectures in first week, right? So you borrow certain amount of money, 10,000 from a money lender, who charge a monthly interest rate 5%. This is huge, right? Monthly interest rate 5% is huge. Anyway, so we don't care. Okay, so suppose he charge you this. Given that your monthly payment for the loan is 1,000, it will take you slightly more than 14 months to clear your debt. Okay, based on the initial capital and the monthly rate, and also the payment. So you want to determine whether 14 months is enough to finish. Okay, so the answer, okay, is true. Well, it turns out you have to do some calculation, right? So here I need you to, you have a help sheet or whatever, right? So you have to, if you don't remember it, write it down in your help sheet. So let C sub k denote the amount that you own after k months. This is very, very similar to some of our examples. So that's why I want to remind you this formula. Okay. So from the lecture, we know we have this formula. So C sub k, that is the amount you own after k months, can be calculated in this way. So it is equal to C, where C is the initial amount you borrowed. In this case, it's 10,000. Okay, and times bracket 1 plus alpha to the power of k. So k is the months, number of months. The alpha is the monthly rate. Okay, minus, and this r. This r is your monthly repayment. So in our example, the r will be 1,000. Okay, and times this fraction. This fraction actually is a sum of geometric series, right? So in the lecture, we derive this formula, right? So now it's time to use it. Okay, so it's clear, right? You know what I'm talking about. So there's a formula you can use. Okay, now in our problem, now let's see what happened after 14 months, because the claim is you need more than 14 months to clear. So in other words, after 14 months, you still own something, right? So, okay, so in our problem, the K is 14, right? K is 14, and all the numbers I already said, right? The alpha is the 5%, so you get 1 plus 0.05, so it's 1.05. And then you just plug in the numbers. And you need a usual calculator, right, with the exponential. So you need those, and you plug in. Hey, the answer is about 200. Okay. Well, maybe it is plus minus a little bit, but it's still bigger than 0. So you still have something. You still own the guy something. Okay? So the claim is true, right? So it takes you slightly more than 14 months. After 14 months, you still own 200. And slightly more means the next payment will be more than enough, right? So that's the answer for this problem. Is this okay? Okay. Good. Now there's one more question in the test. So number 9 is about something which we haven't covered. But number 10 we have covered. Okay. So let's look at the number 10. So it says there are 2 sets. The sets, one is you collect the integers which are divisible by 4. For example, 0, 4, negative 4, 8, negative 8, and so on and so forth. Right? So you collect integers which are divisible by 4. So this is the first set. The second set is all the integers. 1 divided by 7, the remainder is 1. Okay, for example, 8, right? And 15, or minus 15. Okay, so these things belong to the second set. Okay, so we have 2 sets here. Now the claim is these 2 sets have the same cardinality. Okay, so we introduce a concept of cardinality, right? So, okay, so the answer is true. Well, why it is true? So let's call the sets A and B, right? So this is A. The multiple of 4 is A. All the remainder 1 divided by 7 is B. Okay, so we want to show they have same cardinality. But we can show them they all have the same cardinality as the set of integers, right? So I'll show you this is true. The size of A is the same as the size of integers, and so is the size of B. Okay? So now let's set 2 bijections. So how can I match the integers with elements in A? I just multiply 4, right? So this is a bijection. So consider f from Z to A defined by f of n is 4n. So then you are bijection from Z to A, right? Similarly, you send this guy to B by doing this, right? So because the set B is generated by 7 times something plus 1. That's the form of when you divide it by 7, the remainder is 1, right? So when you do this, this is also a bijection. I think it's quite easy to see this is bijection. So we establish the size of A equals size of Z, also size of B equals size of Z, and then they are equal, right? So this is the answer for question 10. I guess that's the rest of the question is talking about games, which we will talk about it after the break, after the 1-week break. Right? Okay, so these are the things I want to say today, and there's no more lecture. I will answer questions if you have questions about notes or tutorials. Okay. And sorry for the guys I'm at home watching. Okay, so that's the end of the lecture.